In this video, we want to talk about the NumPy package, which is, to my opinion, one of the most useful and fundamental packages in Python programming language. And it is used in many different fields. For example, even you are working with images, actually you're working with NumPy arrays. And it has a lot of functions for statistics, linear algebra, and working with random stuff, and etc. And also it's a fundamental package used in machine learning, business intelligence, data science, and a lot of other fields. And here's the general outline of this course, which we're going to cover these topics and a lot of more. And the chapters are included in the description below. If you want to navigate to whatever chapter you want, you can use those chapters as well. So now let's start the NumPy course. So first of all, let's talk about how we can create an array in Python NumPy. So in order to do so, we simply type import NumPy as np. So we import the NumPy package as np. Then we simply type np.array because we want to create an array. And suppose that we want to create a one-dimensional array. So for example, with a bunch of numbers, for example 1, 2, and 3, and let's store that in a variable, let's say called x. And now if I print the x variable, and also if I print the type of the x variable, and if I run the code, you can see that here is our array, and you can see the type of that x variable is NumPy ND array, means n-dimensional array. So in this case, it's a one-dimensional array. And here is a question. What is the benefit of using the NumPy array instead of, for example, Python lists or tuples? So for example, because we can define a list of numbers, for example, 1, 2, and 3. So here is a question. What is the benefit of using NumPy array instead of the lists? So in order to explain this, let's define another list, let's say called B, and it contains a couple of numbers, 2, 2, and 2. And now if, for example, suppose that I want to do an element-wise multiplication. So maybe you say, okay, I can simply type A times B. And now if I run the code, you can see that we get error. Why? Because the lists do not support the element-wise multiplication. But the arrays do support the element-wise multiplication. So for example, we define another variable, let's say called y, and then we simply define np.array. We define a array. So for example, they are 2, 2, and 2. And now if I print x times y, and if I run the code, you can see here's the output. And you can see that one of the benefits of using the NumPy arrays is using the element-wise operations. But now let's talk about another important note, and remember that this is a rule that the elements in the array should be the same type. What do I mean by that? For example, here, if I print the x.data type, d type means data type, I mean the type of the things and stuff which are in our arrays. So now if I run the code, you can see that the data type is integer. You can see all of the values in our array are integers. But here is a question. What is going to happen if, for example, I change the value, this value, I mean 1, to 1, for example, 6? And if I do so, and if I run the code, you can see that the data type is going to be float. Why? Because as I've said, this is a rule that all of the elements in an array should be the same type. So if you want to convert all of these values to a same type, what is going to be that type? Can we convert all of these numbers to integers without losing any information? Of course we can't. For example, if you convert this number to an integer, for example, if you convert it to 2, then you're going to lose information because it was not 2, it was 1.6. But for example, if you consider a fractional part of 0 for this number, you're not going to lose any information. So if you convert all of these numbers to floats, you're not going to lose any information. But if you convert all of these numbers to integers, of course, you're going to lose information because you are converting 1.6 to 2. And that's exactly the reason that the data type of this array is going to be float. And once again, if I print the x itself, and if I run a code, you can see 1.6, 2.0, and also 3.0. And you can see that all of the values are float. And this characteristic is called promotion. It means that the values are going to be promoted to float because here is a rule that all of the elements in an array should be the same type. And let's take another example. As you can see, we have defined a string inside this array, and as I have told you, here is a rule that all of the elements in an array should be the same type. So what is going to be that same type? Can we convert all of these values to, for example, floats? Of course we can't. We can't convert David to float. What float we are going to convert David? So of course we can't convert David to float numbers, but we can convert all of these values to strings. So for example, we can convert 1.6 to string 1.6. We can convert 2 to a string 2, and we can also convert a 3 to a string 3. So now if I run a code, and you can see that here is our array, and you can see that all of the elements are a string, and here is a Unicode string. So that's it. You can see that it has converted all of the values to strings, because here is a rule that all of the elements of an array should be of the same type. So let's talk about how we can create a two-dimensional array. And by saying a two-dimensional array, I mean a matrix. As you can see, matrix has two dimensions, rows and columns. So the first dimension is rows and the second dimension is columns. So in order to make a matrix like this, we can simply use a two-dimensional array. So as you can see here, we have imported the NumPy package as np. Then I simply type np.array because I want to create an array, and I want to make it a two-dimensional array. So first of all, you should open a square bracket, and you can see that PyCharm closes that square bracket automatically, and then you should press enter, and here we can define the rows. So the first row is 2 minus 3 comma 1, so this is the first row, comma the second row is 2 0 and minus 1, again comma, and the third row is 1 4 and 5. So let's store all the stuff in a variable, let's say called a. So this is the name of our matrix. And now if I print a, and now if I print type of a, and if I run a code, you can see here is our matrix, and you can see that it's a n-dimensional array. And if I want to print the shape of this matrix, I can simply type print, and I can simply type a.shape. So a is the name of our array, and that shape returns the shape of that array. So if I run a code, you can see the output is a 3 by 3. So it is a 3 by 3 matrix. So you can see it's a two-dimensional array because it has two dimensions. This is the first dimension, I'm in rows, and this is the second dimension, I'm in columns. And here is a question: can we put all this stuff in one line, or we should put all this stuff in different lines? So the answer is you can put all the stuff in one line, but it is not more readable. So of course you can put all the stuff in one line, but as you can see, this is not readable. So I prefer this way because it is more readable. So you can see that these are the rows of our matrix. And now let's talk about how to create three-dimensional arrays and higher dimensions as well. So in the previous video, we have defined a two-dimensional array, which is a matrix. So as you can see, matrix has two dimensions, row and columns. So row is the first dimension and the column is the second dimension. So it's a two-dimensional array. So this is the first row. This is the first row of our matrix. This is the second row of our matrix, and this is the third row of our matrix. And as a matter of fact, a two-dimensional array is a bunch of one-dimensional arrays. So as you can see, here is a two-dimensional array, or let's say a matrix, and a matrix is a bunch of vectors. This is the first vector, or as a matter of fact, the first row. This is the second vector, or as a matter of fact, the second row. And this is the third row, or let's say the third vector. So as a matter of fact, a two-dimensional array is a bunch of one-dimensional arrays. And with induction, we can say that a three-dimensional array is a bunch of two-dimensional arrays. And let's take an example. Suppose that we want to create a three-dimensional array with this shape. You can see 2 by 2 by 3. And as I have told you, a three-dimensional array is, as a matter of fact, a bunch of two-dimensional arrays. So here's our two-dimensional array. And as you can see, a two-dimensional array is a matrix. So this is a 2 by 3 matrix. And a three-dimensional array like this is a bunch of two-dimensional arrays, is a bunch of matrices. So let's create a three-dimensional array with this shape in order to better understand all the stuff. So in order to create that, we can simply type np.array, and we should open a square bracket, and also the PyCharm closes the ending square bracket, and I press enter. So that's it. And between these two square brackets, I should define two matrices, and each of those matrices are a 2 by 3 matrix. So our first matrix should have 2 rows and 3 columns. So the first row is, for example, 1, 2, 3, and the second row is 4, 5, and 6. So this is the first matrix, which you can see it has 2 rows. This is row 1, and this is row 2. And as you can see, each row has 3 columns. So as a matter of fact, this is a matrix, and its shape is a 2 by 3 matrix. So this is the first matrix. And we should define another 2 by 3 matrix, because the shape of our 3D array is 2 of 2 by 3 matrices. So that's it. Let's create another one. So again, we want to define a matrix. So for example, these are, let's say, 7, 8, 9. And the second row is, for example, 10, 11, and 12. So this is another matrix. This is the first matrix, and this is the second matrix. And as you can see, our 3-dimensional array is a bunch of 2-dimensional arrays, or let's say a bunch of matrices. So let's sort this in a variable, let's say called b. And now, for example, if I print the shape of b, so b.shape, and if I run the code, you can see the shape of b is 2 by 2 by 3. And also, I can print the number of dimension of b, so I can simply type print b.number of dimension, and if I run the code, you can see the number of dimension is 3. But as it is obvious, A, which is a matrix, is a 2-dimensional array. So if I print the number of dimensions of A, you can see the output is 2 because A is a matrix, so it's a 2-dimensional array. But B is a 3-dimensional array. And again, with induction, you can define higher dimensional arrays as well, but the general idea is the same. Now let's talk about how to convert the types of data in the array. So for example, here we can see that we have defined an array which is called X, and you can see all of the values inside this array are strings, and inside each string we have a number. So suppose that I want to convert all of these values to integers. So in order to do so, I can simply type X, which is our array, and then I want to use the function called astype. It means that I'm going to convert the values inside the X array as the type which I'm going to pass to this function. So for example, suppose that I want to pass integer because I want to convert all of the values into integer. And now if I store the result in a variable, let's say y, and if I print the y variable, and if I run the code, you can see here is the result, and you can see all of the values are integers, and you can verify that by simply typing y.dtype, I mean the data type available in the y array. You can see that it's a integer. So also you can pass other things as well. So for example, if you want to convert all of those values to float, you can pass float, and if I run a code, you can see these values are float, and the data type is also float. And remember that you can pass the desired type in different manners. So for example, instead of using this string, you can pass the float itself, and you can see again we get the same output. And also you can pass integer, and if I run a code, you can see we get the same output. So these are integers. But now let's talk about how to reshape an array. So for example, suppose that here is an array which is called X, and it has 6 numbers in it. And now suppose that I want to reshape this one-dimensional array, so we can verify that this is a one-dimensional array. So if I run a code, you can see the number of dimensions of X is 1. So suppose that I want to convert the shape of this one-dimensional array to a 2 by 3 matrix. So in order to do so, I can simply type x.reshape because I want to reshape the X array into a, for example, a 2 by 3 matrix. So I pass 2 by 3, and remember you can pass that in a tuple manner as well. So let's store the results in a variable, let's say called y, and now if I print the y variable, and if I run a code, you can see here's the output, and we have converted the X array into a 2 by 3 matrix. And also let's take another example. Suppose that I want to change the shape to a 3 by 2. So if I run a code, you can see it's a 3 by 2 matrix. But remember, you can't pass, for example, 3 by 3 because the initial array, which is x, has only 6 elements. So you cannot convert it to an array which needs 9 elements. So a 3 by 3 array, a 3 by 3 matrix needs 9 elements. So you have only 6 elements. So it is not possible to reshape x to this shape. So if you run the code, you will get error, because it is very obvious that it is not possible to convert the x array to this shape. But as you can see, the values inside this matrix has been filled in row-wise manner. What do I mean by row-wise? I mean we have filled the first row, then the second row, then the third row, and etc. But what if we want to fill the values in column-wise manner? I mean first the first column, then the second column, then the third column, and etc. So if you want to do so, I mean if you want to fill the values inside this matrix in column-wise manner, you can pass another argument which is called order for filling, and you can pass f, which means Fortran style. So if you run a code, you can see we have filled the values inside this matrix in column-wise manner. So you can see 1, 2, the first column, then the second column, 3 and 4, and then the third column. And if you want to restore that, you can pass a C in order to fill the values in row-wise manner. So if you run a code, you can see here's the output. And because the default value for the order is C, I mean row-wise manner, so if you want to fill the values in row-wise manner, you can't delete this because the default behavior is row-wise. So now if I run a code, you can see we get the same output. But now let's talk about how we can reshape an array into a column-wise vector and also into a row-wise vector, which is very, very useful also specifically in machine learning. So for example, as you can see here, we have an array which is called x, and as you can see, it's a 2 by 2 matrix. But now suppose that I want to convert the values inside this matrix into a column-wise vector. What do I mean by column-wise vector? I mean a vector, for example here, which has 4 rows but 1 column. So it's a column-wise vector. So one of the things that we know so far is we can simply type x.reshape because we want to reshape the x array, and we want to reshape that into 4 rows and 1 column. And what is this for? This for is the number of elements inside our array. So this 4 is the number of elements inside our array, and this 1 means 1 column. So this is row and this is column. So that's it. And I store the results in a variable, let's say called y, and if I print the y variable and if I run a code, you can see here's the result. And as you can see, we have 4 rows and 1 column. So as a matter of fact, it's a column-wise vector. But also we can use other methods as well. So one of those methods is using the size attribute. So I can simply type x.size, and x.size means the number of elements inside the x. So x.size returns the number of elements inside the x. So for example here, if I print x.size, so let's delete all of these lines, and if I run a code, you can see the number of elements inside the x is 4. So as you can see here, x.size is 4. So it means that we are going to reshape our x into 4 rows, I mean the number of elements, and 1 column. So we are going to convert our array into a column-wise vector. So now if I run the code again, you can see we get the same result. But now let's talk about another method which is very famous and popular, especially in machine learning. And that method is you can replace this with -1. And what does it mean? It means that, of course, we are going to convert and reshape that into 1 column, but how many rows do we need? And this -1 means as much as needed. So for example here, in order to convert this matrix, in order to convert this array into a column-wise vector, of course, we are going to convert it to 1 column, but how many rows do we need? And this -1 means as much as needed. Here we need 4 rows in order to convert that into a column-wise vector. So now if I run a code, you can see again we get the same output. But now let's add a couple of elements to the initial array in order to explain this better. So as you can see here, our array is a 2 by 3 matrix. And I want to reshape that into a column-wise vector. So a column-wise vector has one column. But how many rows is it going to have? It has as much as needed. Here, in order to convert a 2 by 3 matrix which has 6 elements, in order to convert this array into a column-wise vector, we need 6 rows. So this -1 means as much as needed. So now if I run a code, you can see it converts all this stuff into a column-wise vector. And because it has needed 6 rows in order to convert that into a column-wise vector, so -1 means as much as needed. And also we can use the same concept for converting our array, for reshaping our array into a row-wise vector. So for example, suppose that I want to reshape this into 1 row, and how many columns? As much as needed. -1 means as much as needed. So in this way, I'm going to reshape that into a row-wise vector. So now if I run a code, you can see here's the output, and as you can see, here is a 2-dimensional array, which is a row-wise vector. But now let's talk about indexing and slicing in Python NumPy arrays. So as you can see, here is an array, and you can see that these are the indices of these values. As you know, in Python programming language, indexing starts at 0. So Python starts counting at 0. So this is the value at index 0. This is the value at index 1. This is the value at index 2. And this is the value at index 3. And suppose that we want to index to this value. In order to do so, we simply type x, and we pass 0 in a square bracket. It means we want to index to that value. So now if I run a code, you can see the value at index 0 of the x is 60. And for example, the value at index 2 is 114. And also remember that we have negative indices in Python NumPy arrays. So you can see the last element, the index of the last element is -1. The index of this value, which is the value before the last element, is -2, and etc. So for example, this is -3 and -4. And if you want the philosophy of these negative indices, you can see that the first index is 0. If you go to the right, you can see the indices increases. But if you want to go to the left, we don't have any value to the left. So as a matter of fact, we start from the end. So the index of the last element is -1. And if you go to the left, the indices, the negative indices will increase. So -1, -2, -3, and -4. So now, for example, if I want to index to the last element, I can simply type x -1. So now if I run the code, you can see the last element is 40. And now let's talk about slicing in NumPy arrays. So suppose that we want this slice of the array. So you can see the indices of these values is 0 all the way up to 2. So in order to do so, in order to slice to that numbers, so we can simply pass 0 all the way up to 3. And maybe you ask why I have typed 3 and not 2, because this value is exclusive. So if you want to include 2, you should write 3, because this value is exclusive. So now if I run a code, you can see that these are the values. So now let's take another example. Suppose that I want these values. So if I want these values, I can simply pass the values at index 1 all the way up to, and remember that you shouldn't write 3 because this second value is exclusive. So if you want to include 3, then you should write 4, because remember that this value, this second value after the colon, is exclusive. So if I run the code, you can see here's the output. And in this special case, which we want the values from index 1 all the way up to the end of the array, we can simply delete this, and it means that we want the values from index 1 all the way up to the end of the array. So now if I run a code, you can see here's the output. And now suppose that I want the values from the beginning of the array all the way up to index 2. So I can simply type all the way up to index 3. So you can see from the beginning of the array all the way up to index 3. And again, remember that this one is exclusive, so because you want to include 2, we should write 3. So now it is going to index these values, I mean from the beginning of the array all the way up to index 2. And again, remember that this one is exclusive. So if I run a code, you can see here is the output. And here is another question. Can we use negative indices for slicing? Of course we can. For example, suppose that we want to index these values. So as you can see, the indices of these values, if we want to talk about the negative indices, is -4 and -3. So if you want to get this slice of the array, we can simply type the values from index -4 all the way up to -2. Remember that you shouldn't write -3 because this second value is exclusive. You should write -2. So if you want these values with these indices, you should simply type -4 all the way up to -2 because this value is exclusive. So now if I run the code, you can see here's the output. But now let's talk about the slicing and also indexing in a two-dimensional array. So as you can see, this is a matrix, or as a matter of fact, a two-dimensional array, and we want to talk about the slicing and indexing. So again, remember that Python starts counting at 0. So it says this is row 0, this is row 1, and this is row 2. And also this is column 0, column 1, and column 2. So remember, Python starts counting at 0. So suppose that we want to index to this value. So as you can see, this value is at row 2 and column 2. So we can simply type print and x, and the row index is 2, and also the column index is 2. So if I run a code, you can see the corresponding value is 14. And now suppose that I want to index to this value. So you can see the corresponding row for that is 1. And the corresponding column is 0. So now if I run a code, you can see the value is 114. So that's it. But now suppose that I want these values. So as you can see, these values are at row 0. So we simply type row 0. And which columns? The columns are the column 0 all the way up to column 1. So we simply type 0 all the way up to column 2. And remember that because this value is exclusive, you shouldn't write 1, because if you want to include 1, you should write 2 because the second value is exclusive. So now if I run a code, you can see we have indexed these values. And also remember that we can do that in a simpler way. We can delete this, and it means that from the first column all the way up to column 1. And again, remember that this one is exclusive, and because of that reason I say all the way up to column 1, because this one is exclusive. So now if I run a code, you can see here are the values. And now let's talk about another example. Suppose that we want to get this slice of the array, which you can see 10 and 14. So you can see these values are at column 2. So let's put a comma. In the first position, we should talk about the rows, and in the second position, I mean after the comma, we should talk about the columns. So those values are at column 2. So that's it. But which rows we are talking about? So those are row 1 all the way up to row 2. So we can simply type 1 all the way up to 3. And again, remember that this one is exclusive, and because we want to include 2, we simply write 3. So now if I run a code, you can see here is the output, and you can see that we have indexed those values. And also remember that there is a better way, or let's say a simpler way for doing that, and we can delete this, and it means that we want the rows at index 1 all the way up to the end, and also those values are located in the column which its index is 2. So now once again, if I run a code, you can see here is the output. But now let's talk about indexing in a three-dimensional array. So if you remember, I've told you that a three-dimensional array is a bunch of two-dimensional arrays, or as a matter of fact, a three-dimensional array is a bunch of matrices. So you can see this is the first matrix inside that array, and this is the second matrix inside that array. So suppose that I want to index to this one. So if you remember, Python starts counting at 0. It says this is matrix 0, and this is matrix at index 1. So if I want to index this one, I can simply pass x sub 1. And now if I run a code, you can see we have indexed to this element, I mean this matrix. But now suppose that you want to index to this value. So as you can see, this value is in the matrix which the corresponding index for this matrix is 1. So that's it. And inside this matrix, you can see that this value is at row 0, so it is at row 0, and also column 1, so we pass 1. So now if I run a code, you can see here's the output, and you can see that we have indexed to this value. But now let's talk about a very important terminology, which we are going to use that terminology in future parts. And that terminology and that term, which is very important, is axis. So because we don't have rows and columns for higher dimensions, because rows and columns are for two-dimensional arrays. So row is the first dimension and column is the second dimension. So for higher dimensions, for example, like a three-dimensional array, a four-dimensional array, and etc., we don't have rows and columns. So if we want to use a general term for all of the dimensions, for example, for one-dimensional, for two-dimensional, for three-dimensional, and etc., we use the word, or let's say the term, axis. So for example, we say that this is axis 0, axis 1, and axis 2. So now let's talk about Boolean mask indexing. And suppose that we want to filter out those values in this array which are even. And as you know, the even numbers are divisible by 2. And when I say they are divisible by 2, I mean when you divide those numbers by 2, the remainder would be 0. So for example, 5 is not an even number. So when you divide that by 2, the remainder would be 1, not 0, because it is not divisible by 2. But for example, 12 is divisible by 2, so if you divide that by 2, the remainder would be 0. So in order to check whether a number is even or odd, you should check whether it is divisible by 2 or not. So let's do that. So in order to do so, we simply type x modulo operator and 2, which returns the remainder when we divide by 2. And we want to check whether this one is equal to 0. So let's print this. If I print this and if I run the code, you can see for the first one it is true because it is an even number. For this one it is false, and for this one it is false. For this one it is true. For 12 it is true, and also for 14 it is true. And let's store this in a variable, let's say called mask. And what do I mean by mask? As a matter of fact, mask is a bunch of true-false values which determines whether a condition is true or not. So as a matter of fact, our masks determine whether a number is even or not. So now we want to print the even numbers from the x array. So we simply type x and we want to index to those values which are even. So we use the mask. So this is called Boolean mask indexing. And as you know, our masks determines whether a number is even or not. So x sub mask returns the values which are even, which satisfy this condition. So now if I run the code, you can see these are the even numbers. But now let's suppose that we add a value, for example, a couple of negative values. So for example, -4, -2, and for example, -8. And now suppose that we want to filter out those values which are divisible by 2 and also they are positive. So we use the AND operator and we should add the other condition. And the other condition which you want to check is whether that number is positive or not. So we are going to check whether that number is positive and whether that number is divisible by 2. So if all of these conditions was true, then the mask is going to return true. And then we are going to index those values from the x array which satisfy these conditions in the mask. So now if I run the code, you can see here are the values which are divisible by 2 and also they are positive. So now let's take another example. Suppose that this is our array and we want to check whether a number is divisible by 2 or divisible by 3. So in order to do so, we simply type x modulo operator and 2 and is equal to 0. It means if the number is divisible by 2. And we want to check whether a number is divisible by 2 or, and for saying or, we can put a vertical line or so-called pipe in order to say or, and then we want to check, so we want to check whether a number is divisible by 2 or divisible by 3. So in order to check whether a number is divisible by 3, we can simply type x modulo 3 is equal to 0. So we are saying if the number is divisible by 2 or divisible by 3. and we store that in a variable, let's say called mask, and here we are using that mask in order to index those values which satisfy this condition. And this type of indexing is called Boolean mask indexing, because these masks are Boolean values, true false values. So now if I run the code, so you can see it returns those values which are divisible by 2 or divisible by 3. So for example, if I add another number, which is 9, as you can see, 9 is not divisible by 2, but it is divisible by 3. So if I run the code again, you can see it returns 9 because it is divisible by 3. And now let's take another example. And as you can see, once again, I have added some negative numbers, and I want to filter out those values which are positive, and they are divisible by 2 or divisible by 3. So this is a condition for saying whether they are divisible by 2 or divisible by 3. So this is the condition, but we want to say it should be positive as well. So we put a parenthesis around it, and we want to end this condition with the condition of being positive. So it should be positive, and it should be whether divisible to 2 or divisible to 3. That's it. And we put all the stuff in a variable, let's say called mask, and we are using the Boolean mask indexing in order to filter out those values which satisfy this condition. So now if I run a code, you can see here is the output. And as you can see, it returns the values which are divisible by 2 or divisible by 3, but they are positive. But now let's talk about the arange function in the NumPy package. The arange function simply returns a range of numbers. So for example, if you pass 1 and 5, then it is going to return a range of numbers from 1 all the way up to 5, but not 5 itself. Remember that this value is exclusive, and by default, the step is 1. So by default, the step is 1. So now if I store the result in a variable, let's say called x, and if I print the x variable, and if I run a code, so as you can see, it returns 1 all the way up to 5, but not 5 itself, with a step of 1. So you can see 1, 2, 3, 4, and as you can see, the step is 1. But for example, if you pass 5.1, then it means that you want all the values, you want a range of numbers from the 1 all the way up to 5.1, but not 5.1 itself, with a step of 1. So as I've said, the default step for the arange function is 1. So it means you want all the values from 1 all the way up to 5.1, but not 5.1 itself, with a step of 1. So now if I run the code, you can see here are the results from 1 all the way up to 5. And as you can see, all the values are floats because this value is float. So now if we pass the third argument, which is the step, so for example, if we pass 0.5, which is the step, it means that we are going to return a range of numbers from 1 all the way up to 5, but not 5 itself, with a step of 0.5. So now if I run a code, you can see it returns a range of numbers from 1 all the way up to 5, but not 5 itself, because 5 is exclusive, with a step of 0.5. So you can see 1, 1.5, 2, 2.5, 3, 3.5, 4, and 4.5. So now let's talk about some notes. And if you pass just one number to the arange function, for example, if you passed 5, then the starting point, by default, the starting point is going to be considered as 0. So this is equivalent to passing range of 0 all the way up to 5, but not 5 itself. So if you pass just one number to the arange function, then the starting point is going to be considered as 0 by default. And as you know, the step is again by default 1. So here it is going to return all the values from 0 all the way up to 5. And as you know, the default step is 1. I mean, when I say the default step, I mean if you don't pass nothing for the step, then the step is going to be considered as 1. So this is going to return all the values from 0 all the way up to 5, but not 5 itself, with a step of 1. So now if I run the code, you can see here is the result. But now, for example, if I pass 5.1, so it means that a range of numbers between 0 all the way up to 5.1, but not 5.1 itself with a step of 1. And now if I run the code, you can see it returns these values from 0 all the way up to 5. And as you can see, the step is 1, and all the values are float because this value is float. But as you know, Python itself has a built-in function which is called range. And one of the big differences between the Python built-in function range and the NumPy arange function is this, that you can't pass a float number to the range function. So the range function doesn't accept a float number for the starting point or the stopping point or the step. So the range function, the built-in Python range function, doesn't support floats, but the arange function in the NumPy package does support the floats. But now let's talk about the linspace function. So as you can see, I've imported NumPy as np. Then I simply type np.linspace, and linspace basically means linear space, means equal space. And for example, if I pass, for example, 0 and 1 and also 11 as an example, it means that I want to generate 11 numbers. I want to generate 11 numbers between 0 and 1. And remember that 1 is also included. So between 0 and 1, I want to generate 11 numbers with equal space, with linear space. So I store the result in a variable, let's say called x. And now if I print the x variable, and if I run the code, you can see here is the output. And as you can see, between 0 and 1, and remember that 1 is included, we have generated 11 numbers. And now let's take another example. So I pass 0 and 2 times np.py, and for example 1000 numbers. It means that I want to generate 1000 numbers between 0 and 2 times pi, and remember that this value is included. And for example, this example is very useful when you want to plot a sine of x, a cosine of x plot, and etc. So now if I run the code, you can see we have generated 1000 numbers between 0 and 2 times pi. But now let's talk about how to create a matrix, for example, a 3x3 matrix like this one, which you can see on the right side, which all of the values are 1. So as a matter of fact, our matrix is a bunch of 1s. So in order to do so, as you can see, first of all, we have imported NumPy as np. Then I simply type np.ones, and I should pass the shape of our matrix in a tuple. So for example, I want to pass a 3x3 because we want to generate a 3x3 matrix. And now if I store the result in a variable, let's say called x, and if I print the x variable, and if I run a code, you can see now we have a 3x3 matrix, which all of the elements are 1. So now, as you can see, by default, the ones in this matrix are floats. So in order to convert them to integers, we can pass another argument to the ones function, which is called dtype, means data type, means the type of data which is in our matrix. And for example, I want to pass, for example, integer in order to make them integers. So if I run a code, you can see now they are integers. And also remember that you can pass that in other ways as well. So for example, you can pass the int itself. So if I run a code, you can see we get the same output. But now suppose that instead of a bunch of ones, we want to generate a bunch of zeros. I mean, for example, a 3x3 matrix, which all of the elements are 0. So in order to do so, we can simply pass another function, which is called zeros. And for example, we want a 3x3 matrix, which all of the elements are zeros. And for example, the data type we want to consider is integer. So now if I run the code, you can see all the values are integers, and it's a 3x3 matrix, which all of the values are integers. And if I remove this, and if I run a code, you can see that by default, the data type is a float. So that's it. And remember that it's very obvious that you can change the shape of your matrix. For example, you want to define a 2x4 matrix, which all of the values are zeros. And also you can do the same thing for the ones function. So you can see it's a 2x4 matrix, which all of the values are 1. Now let's talk about the identity matrix and how to create an identity matrix in NumPy. So as you can see, this is a 3 by 3 identity matrix, but maybe you ask what is an identity matrix. Basically, an identity matrix is a matrix that the diagonal values are 1 and the other values are 0. So this is the meaning of identity matrix. And remember that usually in mathematics, the identity matrix is denoted by I, means identity matrix. So here, as you can see, we have imported NumPy as NP. Then I simply type np.I, and I think they use this specific name for generating the identity matrix because it is pronounced the same way as capital I, which the identity matrix is usually denoted by I in mathematics, means identity matrix. And remember that a lot of programming languages use this name as well. So that's it. We use this function in order to create an identity matrix in NumPy. And now in order to generate a 3 by 3 identity matrix, we should pass 3 and 3. And remember that you shouldn't pass that in a tuple. So if you pass that in a tuple, you will get error. So you can see you get error. Why? Because in this specific function, you shouldn't pass these values in a tuple. You should pass them separately. And as a matter of fact, the syntax of this specific function is similar to MATLAB software. So you should pass that in this way. So remember that in this case, you shouldn't pass that in a tuple. You should pass them separately. So we want to generate a 3 by 3 matrix, which is an identity matrix. So I store the result in a variable, let's say called x. And now if I print the x variable and if I run a code, you can see now we have a 3 by 3 identity matrix. And again, I can pass the D type arguments, and for example, I can pass integer in order to make all the values integer. And also I can pass different values. For example, maybe I want to generate a 2 by 2 identity matrix, which you can see here is the output. But now let's talk about a question. Maybe you ask what would happen, for example, if we pass, for example, instead of a 3 by 3 matrix, we pass, for example, a 3 by 4 matrix. So now if I run a code, you can see that this is a 3 by 3 matrix. This is a 3 by 3 matrix, which is an identity matrix, but you have specified that you want 4 columns. So those columns that are extra are considered as 0. So for example, if you pass, for example, 4 and 3, and if I run a code, you can see this part that I'm showing on the screen is an identity matrix, a 3 by 3 identity matrix. But because you have specified that you want 4 rows, the 4th row is considered as 0. So now maybe you think, how can I generate an empty matrix in NumPy? So in order to do so, you can simply use, for example, the empty function in order to do so. For example, you want to pass a 3 by 3 matrix. And for example, if I store the results in a variable, let's say called x, and if I print the x variable, and if I run the code, so as you can see, this is a 3 by 3 matrix, but as you can see, these values are not empty because it is not possible to generate a 3 by 3 matrix which all of the values are empty. And here is a question, what do you mean by empty? So it is not possible to generate a 3 by 3 matrix which all of the values are empty. But here, as you can see, these values are chosen randomly, completely randomly. And this leads to fast creation of this matrix. And here is the question, what is the benefit and use case of the empty function? And the use case of the empty function is this, that you generate this matrix, and for example, along your program, you want to use, for example, for loops or etc. in order to manipulate these values. So for example, take this simple example. So as you can see, I've created an empty matrix, and then using for loop, I have defined the values inside this matrix. And maybe you say, okay, I can use, for example, the zeros function in order to do so. And for example, in order to create an empty matrix, I can use the zeros function in order to create a zeros matrix. And then I want to use these for loop. So that's true, but remember that the empty function, the creation of the empty matrix is much faster than the creation of this type of matrices. Because, for example, in the zeros function, you have a constraint that all of the values should be 0. But in the empty function, you don't have any constraint. All the values are chosen randomly. And also remember that you can pass whatever d type that you want. For example, I want to pass the integer d type. So if I run the code, you can see the data types, the types of data is integer. So now let's talk about the access arguments in functions in the NumPy package. So as you can see, we have imported NumPy as NP, and also we have created a two-dimensional array. So now suppose that we want to calculate the summation of all these values. So in order to do so, we simply type np, which is the NumPy package, and then I simply use the sum function, and I want to calculate the summation of x, which is our array, and I want to store the result in a variable, let's say called result, and I want to print the results variable. So if I run a code, you can see here is the output, which is the summation of all these values. But now let's talk about how we can calculate, for example, the summation of each row. In order to do these stuff, we should use an argument called access. And because here in this example, in this specific example, we have a two-dimensional array, so we have two possible choices for access. The first one is 0 and the second one is 1. And remember that in a two-dimensional array, which is a matrix, access equals to 0 means along the rows, and access equals to 1 means along the columns. So for example, access equals to 1 means along the columns. So for example, you can see that this is the first column, column 2, and column 3. And we want to calculate the summation along different columns. So column 1, column 2, and column 3. And we want to add these values, which for example in this case, it returns, for example, 6. And also we want to add the values along the columns for this one, which gives us 180. And also we want to calculate the summation of these values along different columns. You can see column 1, column 2, and column 3, which returns 1. So as a matter of fact, access equals to 1 means we want to calculate the summation along the columns, along different columns. So now if I run a code, you can see these are the values, which for example, this is the summation of the first row along different columns, and this is the summation of the second row along different columns, and this is the summation of the third row along different columns. But now let's talk about access equals to 0. So access equals to 0 means along the rows. So for example, for this first column, the summation of the values along different rows is equal to 51. And for this second column, the summation along different rows is 63. And also for this column, the summation along different rows is 73. So now if I run the code, you can see here is the output, which this one is the summation of the first column along different rows, and this is the summation of the second column along different rows, and this is the summation of the third column along different rows. So here is the summary. Remember that access equals to 0 for a two-dimensional array, for a matrix, means along the rows, and access equals to 1 means along the columns. But now let's talk about a three-dimensional array and how to interpret different axes value. So remember that because we have a three-dimensional array, there are three possible values for the axis arguments. Those are 0, 1, and 2. But now let's talk about axis equals to 0. So axis equals to 0 means along different matrices, because if you remember from previous parts, we have said that as a matter of fact, a three-dimensional array is basically a bunch of matrices. So you can see this is matrix 1 and this is matrix 2. So as a matter of fact, a three-dimensional array is basically a bunch of matrices. And here the summation of x along different matrices means that, for example, 0 from the first matrix plus 4 from the second matrix is equal to 4. This is the result. And 1 from the first matrix plus 5 from the second matrix is 6, and etc. But axis equals to 1 means along different rows in each matrix. So for example, in this specific matrix, if you want to do the summation along different rows, you can see 0 from the first row plus 2 from the second row is 2. And also 1 from the first row plus 3 from the second row is 4. So these are the values for the first matrix. But let's talk about the second matrix. The summation of 4 from the first row plus 6 from the second row is 10, and also 5 from the first row plus 7 from the second row is 12. And these values are for the second matrix. So the summation of x along axis equals to 1 means along different rows in each matrix. And axis equals to 2 means along different columns in each matrix. So we can see the summation of the values in this matrix along different columns is, for example, 0 from the first column plus 1 from the second column is 1. And 2 from the first column plus 3 of the second column is 5. So these values are from the first matrix. And the second matrix, in the second matrix, 4 from the first column plus 5 from the second column is 9, and 6 from the first column plus 7 from the second column is 13. So these values are from the second matrix. So axis equals to 2 means along different columns in each matrix. So in order to summarize, for a three-dimensional array, axis equals to 0 means along different 2D arrays, along different matrices. And axis equals to 1 means along different rows in each matrix. And also axis equals to 2 means along different columns in each matrix. So with induction, I can simply say that for a four-dimensional array, we have 4 possible values for axes. Axis equals to 0 means along different 3D arrays. Axis equals to 1 means along different 2D arrays, along different matrices in each 3D array. And axis equals to 2 means along different rows in each matrix. And axis equals to 3 means along different columns in each matrix. And as you can see, these lines are exactly these lines. But because we have a 4D array, we have added this line as well. And for example, for a 5-dimensional array, it has 5 possible values for the axis. Axis equals to 0 means along different 4D arrays. Axis equals to 1 means along different 3D arrays in each 4D array, and axis equals to 2 means along different 2D arrays in each 3D array. And axis equals to 3 means along different rows in each matrix, and axis equals to 4 means along different columns in each matrix. And as you can see, these lines are exactly these lines, and because we have a 5-dimensional array, we have added this as well. And as it is obvious, you can interpret higher dimensions with induction as well. But now let's talk about min, max, argmin, and argmax. And as you can see here, we have imported NumPy as NP, and here I have defined a one-dimensional array, which is basically a bunch of numbers. And these are the corresponding indices of these values. So you can see that the index of this first value is 0, because as you know, Python starts counting at 0. So this is the value at index 0, this is the value at index 1, and etc. And for example, if I want to calculate the minimum value, I simply type np.min of x. And now let's print the result. So we want to print the minimum value of x, which you can see it is 10. But here is a question: how can we calculate the index of the minimum value? So as you can see, the value which is minimum is 10, but the index of this value is 2. It means that the value which is minimum is at index 2. How to calculate the index of the minimum value? In order to do so, we can use a function which is called argmin. It means that the argument which is the minimum value. So now if I run the code, you can see here is the output which shows the index of the minimum value. And with a similar approach, we can calculate the maximum value of x and the argument which is the maximum value of x, the index of the maximum value. So if I run the code, you can see the maximum value is 600 and the index of that value is 1. But here is a possible question that you may ask, and that question is, what would happen if we have, for example, 2 minimums? So you can see that here we have 210. One is at index 2 and the other one is at index 4. So as you can see, the minimum value is 10, but what about the index of the minimum value? And the answer is NumPy is going to return the first index. So you can see that the first value which the NumPy is encountering with is this value, which the corresponding index is 2, so it is going to return 2, not 4. So if I run the code, you can see it returns 2 because this is the first index. This is the first value which the NumPy encounters with. So now let's talk about the sort function and also the argsort function. So as you can see, we have imported NumPy as NP, and also we have created an array which is called x, which is a bunch of numbers, and these are the corresponding indices for these values. And remember that Python is start counting at 0, so the first value, the index of the first value is 0, the index of the second value is 1, and etc. So in order to sort these values in ascending order, we simply type np.sort because you want to sort the values of x. And then, for example, suppose that I want to print the results. So if I run the code, you can see here's the results, which you can see this is the sorted array, which you can see that these values have been sorted in ascending order. But what about the argsort? Basically, the argsort returns the indices of these values. So what is the index of 10? So as you can see, the index of 10 is 2. Then the index of 14, as you can see, is 3, and the index of 50 is 0, and the index of 600, as you can see, is 1. So if I print np.argsort of x, and if I run the code, you can see here is the argsort output, which you can see it is exactly this one. And basically the output of the argsort means if you want to sort the values in the ascending order, you should put the corresponding values of these indices one after each other, exactly in this order, to make the sorted array. So if you want to sort the values, you should put the corresponding values of these indices one after each other in order to make the sorted arrays. So basically, these are the corresponding indices of the sorted array. But here is a question: how can we do all this stuff in descending order? In order to do so, first of all, let's delete this line. In order to do so, we should open a square bracket, and also we should close the square bracket, and then we simply put 2 colon, and we should pass -1. Basically, this is somewhat an indexing. It means from the beginning of the array all the way up to the end of the array with a -1 step. And with a -1 step, it means we are reversing this. So we are reversing this, and basically, so this basically means we're reversing all the stuff. So if I use this for the argsort as well, and if I run the code, you can see we have reversed the sorted array, and also we have reversed the argsort output. So basically, these are the output for sorting in descending order, and the output of the argsort for the descending order. But now let's talk about the unique function in the NumPy package. So as you can see, I have defined an array which is called x, which is a bunch of strings A, B, and C. And suppose that I want to calculate the unique values in x. So in order to do so, I simply use the unique function in the NumPy package, and I pass x, and I want to store the results in a variable, let's say called u. And here I want to print the u variable, which is the unique values. And as you can see, this is the result, which is the unique values in x. But now let's talk about how to calculate the corresponding counts of these unique values. So as you can see, the corresponding count of a should be 3 because we have 3 of that. The corresponding count of b should be 1 because we have 1 of that. And the corresponding count for c should be 2 because we have 2 of that. So that's it. In order to do so, I pass another argument, which is called return counts, and I pass true. Basically, it means that we want to return the counts as well. So I store the result in another variable, which is called c, because now this function returns 2 values. The first one is the unique values, and now the second one is the counts, the corresponding counts. So let's print the corresponding counts as well. And if I run the code, you can see these are the corresponding counts for these unique values. And now if you want to get a better looking result, you can combine whatever you've learned in Python in order to make the result more beautiful. For example, suppose that you want to get a dictionary from these values. So in order to do so, you can, as I said, you can combine whatever you've learned in Python. So for example, you can simply use the zip function, and you want to zip U and C, I mean the unique values and their corresponding counts. And then you pass that to dict function in order to convert that to a dictionary. And now let's print that dictionary. And now you can see here is the result. It says that the count of A is 3, the count of B is 1, the count of C is 2. And as it is very obvious, you can change these values, and for example, you can pass numbers in order to calculate the unique values and their corresponding counts. So if I run the code, you can see here is the results, and these are the unique values 10, 20, and 30, and these are the corresponding counts of each unique value. But now let's talk about the statistics and how to calculate mean and median. So as you can see, here are some marks, for example, for some students from 20. And suppose that we want to calculate the mean and also the median of these marks. So now let's talk about how to calculate the mean of this data. So in order to do so, I print np.mean of x. I mean, we want to calculate the average, or let's say the mean of x. So if I run a code, you can see here's the output, which is the average of these marks. And basically the formula for calculating the average is summing these values. So you should sum these values, all these values, and divide that by the number of values. So as you can see, we have 5 values, so you should sum these values and divide that by 5, because the number of elements is 5. And the result would be the mean of x. So now let's talk about how to calculate the median. And remember that I'm going to talk about the theory of calculating the median by the end of this part. But now let's do it in Python, and later on we are going to talk about the theory of calculating the median as well. So in order to calculate the median, I simply use the median function in order to calculate the median of x. So if I run a code, you can see the median of x is 18. So once again, let's print the mean of x. So np.mean of x. And if I run the code, you can see that here's the mean, I mean the average, and here's the median. So if you look at this data, you can see that obviously we have an outlier, which is this one. So you can see that the norm of data is around 18. But you can see that this value is an outlier. And remember that the mean is more sensitive to outliers, but the median is less sensitive to outliers. And this is one of the benefits of using median instead of mean for calculating and measuring the centrality of data. But now let's talk about the theory for calculating the median. So as you can see, here is a list of numbers, and we want to calculate the median of this data. So the first step is we should sort the values in ascending order. So you can see that we have sorted these values in ascending order. And if the len of this data is odd, I mean if the number of this data is odd, so we can see that we have a 1, 2, 3, 4, and 5 data. And it is very obvious that 5 is an odd number. So if the len of data, I mean if the number of data is odd, you should pick the middle value. So you can see that the middle value is 18. So this is the median of this data. But what would happen if the len of data is not odd and it's even? So consider this example. So you can see that we have 1, 2, 3, and 4 data, and 4 is very obvious that it's an even number. So the first step is to sort the values in ascending order. So let's do it. So you can see that we have sorted the values in ascending order. And if the len of data, I mean if the number of data is even, you should average the middle values. So here, because we have 2 middle values, so you can see that we have 2 middle values, we should average these values, average these middle values. So we do that, 17 plus 18 divided by 2 is 17.5, and this is the median of this data. So let's verify that. As you can see that this is the first example, which the median is 18, and for example, if I remove this. And if I run the code, you can see that this is the second example, which you can see that the median is 17.5. So now let's talk about the standard deviation, which is a measure for calculating the amount of variation, or let's say dispersion. So for example, here in this data, you can see that we don't have any variation. All of the values are 20. But for example, in this example, you can see that we have some variation because all of the values are not the same. So there is some variation in this data. And one of the most well-known measures for calculating the variation in a data is the standard deviation, which we are going to talk about the theory of that by the end of this part. But now let's do it in Python. So as you can see, we have imported NumPy as NP, and also we have defined two lists, which are some numbers, and we want to calculate the standard deviation of x and also the standard deviation of y. So in order to do so, I simply type NP, which is the NumPy package. Then I use the std function, means a standard deviation, and I should pass the x in order to calculate the standard deviation. So if I store the results in a variable, let's say called std, and if I print the std variable, and if I run the code, you can see here is the standard deviation of x. But now let's calculate the standard deviation of y, which is basically 0, but now let's do it in Python as well. So if I run the code, you can see the standard deviation is 0. But remember that this standard deviation function has another argument, which is called DDOF, which is a very important argument. And for example, if you pass 1, then you're going to calculate the sample standard deviation. And if you pass 0, then you're going to talk about the population standard deviation. And now let's talk about what is sample standard deviation and what is population standard deviation in the theory. So now let's talk about the sample and population concept in statistics. Suppose that we have a school which has 500 students. And suppose that we want to study their heights, for example, the mean of their heights, the standard deviation of their heights, and etc. So one of the first approaches for doing so is to study each student individually. So as a matter of fact, we are going to study all these students, all 500 students. But as you can see, it takes a lot of time and a lot of effort. And the other approach is to take a sample. For example, suppose that we take a sample of size 30. I mean, we sample 30 students and we measure their heights, and for example, maybe measure the mean of their heights, the standard deviation of their heights, and etc. in order to generalize whatever we have achieved in the sample to the population, because studying the population itself is very time consuming. We have sampled, for example, 30 students, and we are studying those 30 students in order to generalize whatever we have achieved in the sample to the population, because it is easier to study a sample instead of the whole population. So now let's talk about the sample standard deviation and its formula. So as you can see, this is the formula for calculating the sample standard deviation. Every data minus the mean to the power of 2. And we should add these values and divide by n minus 1. I mean the number of values minus 1. And then finally, we should take the square root of that in order to calculate the sample standard deviation. So here is an example. Suppose that our data is 2, 1, 0. So as you can see, the mean is 1. And the sample standard deviation is each data minus the mean. So 2 minus mean to the power of 2 plus 1 minus 1 to the power of 2 plus 0 minus 1 to the power of 2. So actually, every data minus the mean to the power of 2. And we are adding these values and dividing by the number of the values minus 1. So the number of values, you can see that we have 3 data, so 3 minus 1. And then we take the square root of that, and the result is 1. So here, the sample standard deviation is 1. But now let's talk about the population standard deviation, and the only difference is this one. You can see that in the denominator, it is not n minus 1, it is n. So this is the only difference between the sample standard deviation and the population standard deviation. And here is an example. And if we calculate the population standard deviation, you can see here is the result, which is different from the sample standard deviation. So as you can see, here is the formula for sample standard deviation, and here is the formula for population standard deviation. And as you can see, the only difference is in the denominator. And generally speaking, the formula for calculating the standard deviation is this. As you can see in the denominator, we have n minus something, and that something is called DDOF in the NumPy package. It means delta degree of freedom. So basically, if DDOF is 1, then you are calculating the sample standard deviation, and if the DDOF is 0, then you are calculating the population standard deviation. So here you can see this is our data, and we want to calculate, for example, the population standard deviation. So in order to do so, we should pass DDOF equals to 0. So now if I run the code, you can see here is the population standard deviation. And for example, if I pass 1, it means that I'm calculating the sample standard deviation. So this is the value for the sample standard deviation. So first of all, suppose that I want to define these two matrices. So in order to do so, first of all, we should import the NumPy package. So I import NumPy as np, and then I simply type np.array because you want to create an array. And remember that matrices are a two-dimensional array because they have rows and columns. So they are two-dimensionals, row and columns. So that's it. And in order to define a matrix, I open a square bracket, and you can see that PyCharm closes the square bracket automatically, and then I press enter, and here I should define the first row, which is 0, 1, and the second row is 2 and 3. And I want to name this matrix, let's say, called A. As you can see, we have defined our matrix A. And now let's define this matrix, which is matrix B. So I simply type B, which is our matrix, and then I simply type np.array, and I open a square bracket. And you can see that PyCharm closes the square bracket automatically. And then I need to define the first row, which is 1, 1, and the second row, which is 2 and 3. And now let's talk about how we can add these matrices. So that's very easy. So let's print. So we want to add A and B. So I simply type A plus B. So I'm going to add these two matrices. So if I run the code, you can see here is the result, which is the addition. And if I simply type A minus B, you can see that here is the subtraction. For example, as you can see, 0 minus 1 is negative 1. 1 minus 1 is 0, 2 minus 2 is 0, and 3 minus 3 is 0. So you can see it's correct. And also remember that, for example, if you simply type A plus 5, it means that we are adding 5 to every element in the A matrix. So if I run a code, you can see the result is 5, 6, 7, 8, which you can see that we have added 5 to each element in the matrix A. And also we can do the same thing for subtraction. So for example, if I simply type A minus 5, it means that we are going to subtract 5 from each element of matrix A. And for example, if I want to multiply every element of matrix A by 2, I can simply type A times 2. So if I run a code, you can see here is the result. And now let's talk about how we can multiply these two matrices. By saying multiplying these two matrices, I mean matrix multiplication. In order to do matrix multiplication, that's very easy. I can simply type A, and I should put a @ sign, so that's it, and B. So A @ sign B. That's it. And if I run the code, you can see here's the matrix multiplication of A and B. And also, in order to do matrix multiplication, there is another way. You can simply use the NumPy package. So I can simply type np.matmul, which is a function, and we can see that it stands for matrix multiplication. We want to multiply these two matrices, so I simply pass A and B because I want to multiply these two matrices. So that's it. If I print the result and if I run a code, you can see here's the result, which is exactly correct. But now if you want to do element-wise multiplication, not matrix multiplication, that's very easy. We can simply print A times B. This is an element-wise multiplication. So if I run a code, you can see here's the element-wise multiplication. You can see 0 times 1 is 0. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. So now let's talk about how can we transpose a matrix. So suppose that I want to transpose the matrix A. So that's very simple. I can simply print A dot T, and remember that it should be capital T. So it means transpose. And now if I run the code, you can see here's the transpose of matrix A. And also there is a second approach. We can simply use the transpose function in the NumPy package. So I can simply type np.transpose because you want to transpose matrix A. And if I run the code, you can see again, that's exactly the same result. And now let's talk about how we can calculate the determinant of a matrix. So for example, suppose that I want to calculate the determinant of matrix A. So that's very simple. I can simply print, so little space, and then I simply type np, which is the NumPy package, the alias name for the NumPy package. And then I simply type linear algebra, because this NumPy package has different sections for doing a lot of stuff. For example, it has a section called random for doing random stuff, and also it has a linear algebra section which is used for doing linear algebra stuff. So I want to use the linear algebra section of this NumPy package, and I want to use a function which is called det, means determinant. So I want to calculate the determinant of matrix A. So now if I run the code, you can see here is the result, which is the determinant of matrix A, and you can see that it is true because 0 times 3 is 0, minus 2 times 1, which is 2, so minus 2 is this, -2. And if I want to calculate the inverse of a matrix, that's very easy. I can simply use the inverse function, inv. So I want to calculate the inverse of matrix A. So if I run the code, you can see here's the inverse matrix of matrix A. And now let's talk about how can we calculate the eigenvalues and also eigenvectors of a matrix. So for example, suppose that I want to calculate the eigenvalues and eigenvectors of matrix A. So I can simply use np.linearalgebra. I want to use the linear algebra section of the NumPy package. And then I want to use the eij, I means eigen, and I want to calculate the eigenvalues and eigenvectors of matrix A. So it returns two outputs. The first one is the values, I mean the eigenvalues, and the second one is the vectors, I mean the eigenvectors. So now if I print the values, and also let's print the vectors, and now if I run the code, you can see that this is the first eigenvalue, and the corresponding eigenvector is this, and the second eigenvalue is 3.5, and the corresponding eigenvector is this. But you know, there were a lot of cases, for example, like principal component analysis and, for example, discriminant analysis, which we need to sort the eigenvectors and eigenvalues. By sorting eigenvalues, I mean from larger to smaller. But now we want to sort the eigenvalues and their associated eigenvectors. So for example, this is larger, and we want to put this first, and then we want to put this after that, because this is a larger eigenvalue. So we want to sort the eigenvalues, I mean from larger to smaller, and their associated eigenvectors. So for example, if I put this at first, I want to put the corresponding eigenvector as well at the first position. So let's do that. But now let's print something. So I simply print values.argsort. So let's do that. And if I run the code, you can see here is the result. But what does it mean? It means that when you sort the eigenvalues, so you can see these are our eigenvalues. So if you sort the eigenvalues in ascending order, by saying ascending order, I mean from smaller to larger, which is the default format in Python programming language. So if you sort the eigenvalues in ascending order, the first value would be the value at index 0, and the second value would be the value at index 1. So if you want to sort the values of this array, we should put the values in this order. I mean, we should first of all, we should put the value at index 0, and then we should put the value at index 1 in order to make something which is the sorted version of these values. So that's it. Here's the meaning of argsort. So as you can see, the argsort returns the corresponding index of the sorted values. And by saying sorted values, I mean sorted by ascending order. In ascending order, I mean. So that's it. And as you know, we want to sort the values in descending order from larger to smallest. So that's very easy. We can reverse whatever we have get from ascending order. So in order to reverse all this stuff, we should do this. We should put 2 semicolon and -1. It means from the beginning all the way up to the end, and with a step of -1. So this will reverse all the stuff. So values.argsort returns the corresponding index of the sorted values in ascending order, but if you want the descending order, so we should reverse it. So now if I run the code, you can see here is the result 1 and 0, which is the corresponding index for sorted values in descending order. So now let's store this in a variable, let's say called index. So I define a variable, let's say called index. So this is the corresponding index of the sorted values in descending order. And now we want to update our eigenvalues and eigenvectors using this index in descending order. So that's very easy. I can simply use values, and then you want the values to be sorted in this order, I mean index. And then I store the results in a variable, let's say called values. So I'm updating the values. That's it. And also I want to update the vectors, all the rows, but which columns? The index columns. So from the vectors variable, we want all the rows, but the order of the columns should be according to this index variable. That's it. So I store the result in a variable, let's say called vectors. So as a matter of fact, I'm updating the vectors variable. So that's it. So now if I run the code, you can see that the eigenvalues and their associated eigenvectors has been sorted in descending order. As a matter of fact, we have sorted eigenvectors based on eigenvalues in descending order. So now let's talk about the deep copy and view in the NumPy package. So as you can see, I've imported NumPy as NP, and I have defined an array, a one-dimensional array. And for example, if I define something like this, if I simply type y is equal to x, and now if I print the x variable, and also if I print the y variable, and if I run the code, you can see that these two variables, I mean x and y, are the same. And also we can print the ID of x and also the ID of y, and remember that ID of x returns the location in the memory which this variable is located. So if I run a code, you can see that these two variables are located at the same location in the memory. But you should pay attention that, for example, if you run the code again, then the location would change, but you can see that the locations of the two variables are again the same. So if you run the code again, yes, it is going to be different. I mean, the locations are going to be different, but these two variables, the location of these two variables are exactly the same. And maybe you ask why the locations are different in different runs, because for example, when you run the code just now, for example, a location in the memory is empty, so you store these two variables in that location. But for example, when you run the code, for example, 2 minutes later, maybe that location is not empty, so you are going to store these two variables in another location in the memory. And also, let's talk about another interesting topic. So for example, if you change the value at index 0 in the x variable, for example, to 6,000, and now if I print the x variable and if I print the y variable, and again, remember that we have changed the x variable, not the y variable. But if you run the code, you can see that the y variable has also been changed. And the reason for this is because x and y are exactly the same and they're pointing to the same location in the memory. And for example, in order to fix this problem, you can use something called deep copy. So in order to do so, I simply type x.copy. It means that I want to make a deep copy of the x variable, and I want to store that deep copy into a variable, let's say called y. And now, because I have made a deep copy, so the x variable and the y variables are independent. So if I change the x variable, then the y variable is not going to change. So if I run the code, you can see that here is the x variable. As you can see, it has changed, but as you can see, the y variable hasn't changed because they are independent, because we have made a deep copy. And also remember that in the deep copy, variables point to different locations in the memory, so they are totally independent. So if I run the code, you can see that x and y are located in different locations in the memory. So far we have talked about y equal to x and also the deep copy. But there is another thing which is called view, which is somewhat similar to this one and also somewhat similar to this one. So let's talk about that. So here I simply type y is equal to x.view. It means that I'm going to create a view of the x variable, and I'm going to store that in a variable, let's say, called y. And I'm going to talk about what is the view meaning. So first of all, let's print the ID of the x variable and also print the ID of the y variable. And if I run the code, you can see that they point to different locations in the memory. So it is similar to a deep copy because the two variables point to different locations in the memory. But for example, if I change the value at index 0 in the x variable, for example, to 6,000, and if I print the x variable, and also if I print the y variable, and if I run the code, you can see not only the x variable has changed, but also the y variable has changed. So this property is similar to typing y equals to x. And maybe you ask, what is the application of these topics? I mean, deep copy and view, I mean, shallow copy. And this is the thing that you're going to see in future parts of this series. So for example, there are some functions which they do the exact work, but for example, one of them returns a deep copy and also the other one returns a shallow copy. So as I've said, you are going to see some examples of these topics in the future parts of this series. So now let's talk about the ravel, and I'm going to explain what do I mean by ravel. So as you can see, first of all, we have imported NumPy as NP, and also we have defined a two-dimensional array, I mean a matrix, which you can see the first row is 1, 2, 3, and the second row is 4, 5, 6. And remember that when I say ravel, I mean I want to flatten these values. I mean, I don't care about the shape of this matrix, but I would just want the values inside this matrix, and I want to store all the values inside this matrix in a one-dimensional array, like a list. So for example, I want to get an output like this, for example 1, 2, 3, and 4, 5, 6. So I want to ravel, I want to flatten, I want to get all the values inside the X matrix, and I want to convert them into a one-dimensional array, or let's say something like a list. So in order to do so, that's very easy. I can simply type x.ravel, and for example, I store the results in a variable, let's say called y. Now if I print the y variable, and if I run the code, you can see here's the output, and as you can see, we have flattened these values and we have get this output. And let's talk about a very important note, and that note is this, that you should remember that the output of the ravel function is a view. So if you don't know about what is the difference between view and deep copy, you should watch the corresponding part of this series, which we have talked about view and deep copy and etc. So that's it. So remember that this returns a view. So as a matter of fact, for example, if I change the value at index 0 to, for example, 1000 in the y variable, because the output is view, you can see that if I print the y variable and also if I print the x variable, but remember that we haven't changed the x variable, but because this is a view, because the ravel returns a view, so if I run a code, you can see the x itself has also changed because the ravel function returns a view, not a deep copy. So when I'm changing the y variable, the x variable is also changing because they are a view of each other. And also let's talk about another note, and that note is you can write this one with a function in the NumPy package as well. So you can simply type np.write ravel, and you can use the ravel function, and you want to ravel the x, and for example you want to store that, the result I mean, in a variable, let's say called y. So these two lines are equivalent. So for example here, if I print the y variable, and let's delete one of them, and if I run the code, you can see here's the output. But here is a question that you may ask, and that question is, here we are flattening all this stuff row-wise. I mean, we are putting the values in the first row, then the values in the second row. Maybe you say I want to put all the values in the first column, then the second column, then the third column, and etc. So you want to do all this stuff column-wise. How can we do it? In order to do that, we can simply pass another argument, which is called order, and we want to use a column-wise format, so we should pass f means Fortran like. So if I run a code, you can see here are the values in column-wise format. You can see 1, 4, then the second column, 2, 5, and then the third column, 3, 6. So that's it. And for example, if you pass c, which is the default argument, when I say default argument, it means that if you delete this, it is equivalent to passing order equals to c. So if I run the code, you can see it does all this stuff in the row-wise manner. And remember that, as I've told you, this ravel function in the NumPy package is equivalent to the ravel method. So here we can also pass an argument which is called order, and you can use, for example, f in order to do all this stuff in column-wise manner. And for example, if I run the code, you can see here's the output. So remember that both the ravel function in the NumPy package and this ravel method has an argument which is called order, which defines the order in order to fill the values in that one-dimensional array. So now let's talk about the flatten function, and the flatten function is very similar to the ravel function. So here if I simply type x.flatten, and if I store the results in a variable, let's say called y, and now if I print the y variable, and if I run the code, you can see the output is exactly the same as the ravel function. So the flatten function is very similar to the ravel function. And also, like the ravel function, it has an argument which is called order, which you can pass f in order to do all this stuff in column-wise manner, and also you can pass c in order to do all this stuff in row-wise manner. And remember that order equals to c is the default argument. But the difference between the flatten function and the ravel function is this, that the flatten function returns a deep copy, not a view. So here, for example, if I change the value at index 0, the y variable, and for example, let's change it to 1000, and here if I print the y variable, and also let's print the x variable, and if I run the code, you can see the y variable has changed. You can see the value at index 0 has changed in the y variable, but you can see that none of the values in the x variable has changed, because this returns a deep copy, not a view. So now let's talk about the insert function in the NumPy package. So suppose that we want to insert a number, for example 600, in this position. And remember that Python starts counting at 0. So this position is index 0. So in order to do so, we simply type np.insert, because you want to insert something. And first of all, we should pass the array, which is x, and then we should pass the index. So we want to insert something at index 0, and then we should pass the value. So the value is, for example, 600. So if I store the result in a variable, let's say called y, and here if I print y and if I run the code, you can see that we have inserted 600 at index 0 of this array. And also remember that if we pass, for example, a list of numbers, for example 600 and 700, and if I run a code, you can see that we have added 600 and 700 at the beginning of the array. And for example, if I want to get something like this, if I want to insert something at the end of this array, I can simply pass len of x, and if I run the code, you can see that we have added 600 at the end of that array. And now suppose that we have a matrix and we want to insert a row to this matrix. In order to do so, we simply type np.insert, and we want to insert to this x. So first of all, we should pass the array itself, and then we should pass the index. So for example, we want to insert a row at the beginning of that array, so we simply pass 0, means at the first position. And then we should pass the values. For example, we want to add, for example, 600, 700, and 800. So this is the row that we want to add at the first position of that array. That's it. And we should simply pass x equals to 0 because you want to add a row. So if I store the results in a variable, let's say called y, and here if I print y, and if I run the code, you can see that we have added this row at index 0. And now suppose that we want to add this row at the end of that array. So in order to do so, here we simply pass x.shape and the 0th element of that shape. So you can see that here we have passed 0, and also here we have passed 0. So if I run the code, you can see that we have added this row at the end of that array. I mean the last row. And also remember that, for example, instead of a list of numbers, for example, if you pass 600, then all of the values are going to be 600. So if I run the code, you can see that all the values are 600. And also we can use the similar way in order to add a column. So for example, if I pass x equals to 1, it means column. So you can see that we are adding a column, add column with index 0. And for example, if you pass a bunch of numbers, 600 and 700, you can see that the first column is 600 and 700. And if you want to add this row at the end of this array, here we can simply pass x.shape, and we should pass 1. Remember that here we have 1, and here we have also passed 1. So if I run the code, you can see that we have added this row at the end of that array, I mean the last column. So now let's talk about the delete function in the NumPy package. So suppose that I want to delete this value, which is at index 0 of this array. In order to do so, I simply type np.delete, and I pass x, which is our array, and the value which you want to delete is the value at index 0. So this is the index, and I store the results in a variable, let's say called y. And if I print the y variable, and if I run a code, you can see here's the output. And as you can see, the value at index 0 has been deleted. And for example, if we want to delete this value, which is at index 1, that's very easy. We can pass 1. And now if I run the code, you can see that value at index 1 has been deleted. So now consider this matrix, which is a 2D array, I mean two-dimensional array. And now suppose that I want to delete the first row of this matrix. In order to do so, I simply type np.delete because we want to delete something. And first of all, we should pass the array, which is x, and then we should pass the index of the row which you want to delete. So you can see that this is row at index 0. Remember, Python is start counting at 0, so we want to delete row 0. And then we should pass x equals to 0 because you want to delete the first row. X equals to 0 means row. So we want to delete the row at index 0. So now if I store the results in a variable, let's say called y, and if I print the y variable, and if I run the code, you can see the first row has been deleted. And for example, if you want to delete the first column, I mean the column at index 0, that's very easy. We can pass 1. So x equals to 1 means column, and we want to delete the 0th column. So we store the results in y, and now we're printing y, and if I run the code, you can see that the first column, I mean column at index 0, has been deleted. And again, remember that that's very obvious that, for example, you can delete the column at index 1. So in order to do so, you pass 1. It means that you want to delete the column at index 1. So if I run the code, you can see column at index 1 has been deleted. So now let's talk about how to concatenate NumPy arrays. So as you can see here, we have defined a matrix, a 2x3 matrix, and also here we have defined a 1x3 matrix. As a matter of fact, this is a row vector. And suppose that I want to add this row to this matrix and build something like this. So that's very easy. In order to do so, I can simply type np.concatenate because I want to concatenate these two arrays. And I can pass them in a tuple, so you can say this is a tuple. So I want to concatenate x and y, and I should pass x equals to 0 because I want to add this row vector as a new row to this matrix. So axis equals to 0 means row. So we want to concatenate these two arrays and we want to stack them in row manner. I want to add this row to this matrix. So we are adding a row. And after doing so, I want to store the result in a variable, let's say called result. And now I want to print the result variable. And if I run a code, you can see here is the result, which you can see that we have concatenated these two arrays in row manner. Row-wise concatenation. But now let's take this example. As you can see now, y is a column-wise vector. So you can see that's a column-wise vector. So now suppose that I want to add this column to this matrix. So in order to do so, I want to concatenate x and y, but in column-wise manner. The column-wise concatenation. So I should pass axis equals to 1. So now if I run the code, you can see that we have added this vector, this column, to the matrix X. But now let's talk about two important notes. And the first note is you cannot pass these values as, for example, 7 and 8 like this, because here X is a two-dimensional array, but y is a one-dimensional array. So it is not possible to pass these values because one of them is a two-dimensional array and the other one is one-dimensional array. So if you run the code, you will get error. So this was the first note. So remember that if the X is a two-dimensional array, then Y should also be two-dimensional array. And note number 2 is you can pass multiple arrays to the concatenate function in order to concatenate multiple arrays. So for example here, suppose that I want to concatenate X, Y, and also Y again. I want to concatenate and add this column to this matrix twice. So now if I run the code, you can see that here is matrix X, and also we have added this column twice. You can see 1 and 2. So you can see that we have added this column twice. And also the final note is instead of using the tuple in order to pass these arrays, you can, for example, pass a list of arrays as well. So now if I run the code, you can see that we get the same output. So now let's talk about the append function. So here we can see that we have a one-dimensional array which is called X. And now suppose that I want to append a value, for example, 100 to this X array. So in order to do so, I can simply type np.append. And I want to append to X, and the value which I want to append is, for example, 100. And now I store the results in a variable, let's say called result. That's it. And here I want to print the results variable. So if I run the code, you can see here is the result. But now suppose that instead of one value, I want to add a couple of values. So in order to do so, I can simply pass, for example, a list of numbers, for example, 100, 200, and 300. So if I run the code, you can see here is the result. And as you can see, these values has appended to the X array. And remember that you can pass other things as well. So instead of passing a list of numbers, so here I can define an array which is called, for example, Y. So I simply type np.array. And this is an array which I want to append to X. So now if I run the code, you can see the values in Y has been appended to X. So now let's consider this example. As you can see, X is a 2x3 matrix and Y is a 1x3 matrix. And now we want to concatenate, or let's say append these values to the X array in row-wise manner. So you can see that we have added this row to this matrix. So in order to do so, I can simply type np.append because you want to append X and Y, and we should pass axis equals to 0 means row-wise. So we want to concatenate these two arrays in row-wise manner. And I store the results in a variable, let's say called results. And now if I print the results variable, you can see here's the output. And as you can see that we have appended X and Y together in row-wise manner. And here if I want to append these values, this column vector to this matrix in column-wise format, I can simply pass axis equals to 1. So now if I run the code, you can see that we have added this column to this matrix in a column-wise format. And the question that you may ask is, what is the difference between the append function and the concatenate function? So the first difference between the concatenate function and the append function is you should pass these values, for example, in a tuple or a list, in the concatenate function. But here, you shouldn't pass these values in a tuple or list. So this is the first difference. And the second difference is in the concatenate function, you can concatenate multiple arrays. So here we can see that we have concatenated 3 arrays. But in the append function, you cannot do so. You can only append 2 arrays. And the third difference is when you don't pass any access argument to the concatenate function, then it is going to consider access equals to 0 as the default argument. So if you don't pass any access argument, then access equals to 0 is the default argument. So now if I run the code, you can see that it concatenates x and y in row-wise manner, because access equals to 0 is the default argument if you don't pass any access argument. But in the append function, if you don't pass any access argument, and if you run the code, you can see that it appends all the values. It appends all the values in x and all the values in y. And it doesn't care about the dimension and about the size and shape of those array. And it appends those values in a one-dimensional array. So the output is a one-dimensional array if you don't pass any access argument. And it is going to append all the values in x and y in a one-dimensional array. So now let's talk about poly1d function, and basically poly1d creates polynomial functions in order to evaluate them and etc. So now let's take this example. As you can see, this polynomial function is a polynomial function with a degree 2. So let's define this example. So the first step in order to define a polynomial function is to store its coefficients in a variable. So let's define a variable, let's say called coefficients. And inside a list, I want to define its coefficients. So as you can see, the first coefficient is 3, the second one is 6, and the third one is 12. But you should notice that these coefficients order should be according to the highest order all the way up to the lowest order. So you can see that here in this polynomial function, the highest order is x to the power of 2, and its corresponding coefficient is 3, and the lowest order is this one, which you can see the coefficient is 12. So remember that these coefficients are according to the highest order all the way up to lowest order. So after defining the coefficients, I simply type np.poly1d. So I want to use the poly1d, and remember 1d means one dimension. It means that it has only one variable. So here you can see that we have only one variable, and that variable is x. So 1d means we have only one variable. That's it. And now we should pass the coefficients. So that's it. And I store the results in a variable, let's say called f1. And now if I print the f1 variable, and if I run the code, you can see here's our polynomial function. You can see 3x to the power of 2 plus 6x plus 12. And if you want to evaluate this polynomial function when x is equal to 0, we can simply pass 0 to this function, this polynomial function. So if I run a code, you can see here is the result. And it means that if you plug in 0 to this polynomial function, you will get 12. And for example, if you plug in 1, and if you run the code, you can see you are going to get 21. And also if you plug in 2, and if you run the code, you are going to get 36, and etc. So now example number 2, suppose that we want to define this polynomial function. So as you can see in this polynomial function, the order is not according to the highest degree all the way up to the lowest degree. So the first step is to convert all the coefficients from the highest order into the lowest order. So here it is. You can see that we have sorted all the terms from the highest order all the way up to the lowest order. Now we want to define the coefficients. So if you want to pass these coefficients from the highest order all the way up to the lowest order, the first value is 4, the second one is 5, and the third one is 4. And now I simply type np.poly1d, and I should pass the coefficients. So I should pass the coefficients, and I want to store the results in a variable, let's say called f2. And now if I print the f2 variable, and if I run the code, you can see here's our polynomial function with degree 2. You can see 4x to the power of 2 plus 5x plus 4. But now let's take this example, example number 3. So we can see that here is a polynomial with degree 3. So the first step is to sort all the terms from the highest order all the way up to the lowest order. So there it is. You can see that we have sorted all the terms from the highest order all the way up to the lowest order. But the important thing is, in this polynomial function, we don't have any x to the power of 2. So because we don't have any x to the power of 2 term, its corresponding coefficient is 0. So now, as you can see, if we want to store the coefficients in a variable, let's say called coef, you can see that the coefficient, the corresponding coefficient for x to the power of 3 is 4. The corresponding coefficient for x to the power of 2 is 0. Then the corresponding coefficient for x to the power of 1 is 5. And the final coefficient is 4. So now we are defining a polynomial function, and we want to store that in a variable, let's say called f3. And here we want to print the f3 variable. So if I run the code, you can see here's the output, 4x to the power of 3 plus 5x plus 4. And for example, if I want to plug in 5 to this polynomial function, that's very easy. I can pass 5, and if I run the code, you can see here's the output. Now I really suggest you to watch this video, which is on the screen now. So now let's talk about the polyfit function in the NumPy package, which basically fits a polynomial function to our data. So in order to do so, I simply type np.polyfit because I want to fit a polynomial function. And first of all, I should pass our data, I mean x and y, and then I should specify the degree, I mean the degree of our polynomial function which you want to fit on our data. So for example, suppose that I want to pass 2, it means a polynomial function with a degree 2. And if I store the results in a variable, let's say called coef, because the polyfit returns the coefficients of that polynomial function with a degree 2. So now if I print the coef variable, and if I run the code, you can see here is the output. And you should remember that these are the coefficients of our polynomial with a degree 2 from the highest degree all the way up to the lowest degree. I mean, this is the coefficient of x to the power of 2, this is the coefficient of x, and this is the constant, which you can see here. So this is our polynomial function with a degree 2. And it is very obvious that you can pass different degrees in order to fit other polynomial functions. So for example, if you pass 3, it is going to fit a polynomial function with a degree 3. If you pass 1, it is going to fit a polynomial function with a degree 1, and etc. But now let's talk about how to plot something like this. I mean, the data itself and the fitted line. So first of all, we should create the polynomial function. So in order to do so, I simply type np.poly1d. And if you remember from previous part, we have said that this poly1d basically takes the coefficient of the polynomial function, and then it creates the polynomial function. And I want to call that polynomial function, let's say called f. And now if I print the f variable, and if I run the code, you can see here is our polynomial function with a degree 2. So basically poly1d takes the coefficient and basically creates a polynomial function. So now let's plot the data. So in order to do so, first of all, I should import the matplotlib package. So I import matplotlib.pyplot as a plt. That's it. And also let's remove this line. And now I simply type plt.scatter because I want to plot a scatter plot. And I should pass our data, which is x and y, and the color of our data points. C means color. The color of our data points is going to be, for example, black. And then I simply type plt.show in order to show the chart. So if I run the code, you can see here is the output. But as you can see, the size of the data points is very small. So let's make them bigger. So in order to do so, I pass another argument, which is s, I mean size, and I want to pass 100. So if I run the code, you can see now it seems better. So that's it. But now let's plot the fitted line. So in order to do so, let's define another variable, which is called xx. Then I simply type np.linspace, and I pass 0, 8, 1000, and it means that between 0 and 8, I want to generate 1000 numbers, and I want to store all the stuff in a variable, let's say called xx. And maybe you ask why 0 and why 8, because as you can see, the domain of our x variable is 1 all the way up to 7. but I'm using 0 all the way up to 8. I mean, for example, 0 is one number before 1, and 8 is one number after 7. So that's it, and this is the reason I'm using 0 and 8. And also I want to define another variable, which is called yy, and I simply pass xx to the f function, and you can see that f is our polynomial function, and xx is the range of numbers. So basically, we want to calculate our polynomial function for every data point in this range. That's it, and here I simply type plt.plot, and I want to plot xx and the y, and the color of our plot, for example, is going to be blue. So if I run the code, you can see here is the output. You can see that these are data points, and this is the fitted line. And we can also provide the label as well. So let's define the label. So the label of this plot is the data points, and the label of this plot is the fitted line. And I simply want to add the legend as well. So if I run the code, you can see now the chart is more beautiful. And again, remember that you can pass other degrees for the polynomial function as well. For example, if you pass 1, and if you run the code, you can see now we have fitted a polynomial function with degree 1, I mean a line, but you can see that it is not very good. So let's pass, for example, another example, degree 3. And if I run the code, you can see here is the output. So now let's talk about how to calculate L1 and L2 norm in Python programming language using the NumPy package. But before that, let's talk about the theory of them. So here, suppose that we have a vector like this, x1, x2. These are the coordinates of this vector. So x1, x2, all the way up to xk. So for example, suppose that we have a vector like this. So this is an example, -1, 2, and 3. And in order to calculate the L1 norm of this vector, we should calculate the summation of the absolute value of xi. For example, in this example, the L1 norm of vector v is equal to the absolute value of -1 plus the absolute value of 2 plus the absolute value of 3, which is equal to 6. And also, if you want to calculate the L2 norm of vector v, we should calculate the square root of the summation of the absolute value of xi to the power of 2. For example, in this example, it is equal to the square root of the absolute value of -1 to the power of 2 plus the absolute value of 2 to the power of 2 plus the absolute value of 3 to the power of 2, which you can see that it is approximately equal to 3.74. So as we have said, this is the L1 norm of vector v, this is the L2 norm of vector v, and also remember that we can generalize this and we can define the norm with order equals to p. So the norm of order equals to p of vector v is equal to this formula. You can see that the summation of the absolute value of xi to the power of p and the whole term to the power of 1 divided by p. For example, if you want to calculate the norm with order equal to 3 of vector v, it is equal to the absolute value of -1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 and the whole term to the power of 1 divided by 3, which is approximately equal to 3.30. And now let's talk about how to calculate the L1 norm and also the L2 norm of vector v in Python programming language using the NumPy package. So first of all, I should define the vector v. So its coordinates is -1, 2, and 3. And in order to calculate the norm, I should simply use np.linear algebra. And linear algebra is one of the sections of the NumPy package. A NumPy package has different sections for other stuff. And one of those sections is linear algebra, which is used for doing linear algebra stuff. And I want to calculate the norm function of the linear algebra section. And I should pass v because I want to calculate the norm of v. And I should pass order equals to 1 because I want to calculate L1 norm. That's it. And I want to store the results in a variable, let's say called results, and I want to print the results variable. And if I run the code, you can see here is the output, which is 6, which you can see it is exactly this one. And in order to calculate the L2 norm, I should pass order equals to 2. And if I run the code, you can see here is the output. And if I want to calculate the ord 3, and if I run the code, you can see that it is exactly this one. And now based on L1 and L2 norm and whatever we have learned so far, let's talk about some distances. So first of all, let's talk about the Manhattan distance. So as you can see, for example, suppose that we have 2 points, P1 and P2, and these are their corresponding coordinates. For example, this is an example. You can see that point 1, and this is the coordinates of point 1, 1, 2, 3, and this is point 2, and these are the coordinates of point 2, 2, 2, and 0. And in order to calculate the Manhattan distance, here's the formula in order to calculate the Manhattan distance between point 1 and point 2. You can see that it is the summation of delta xi. And by saying delta xi, I mean x prime coordinates of point 2 minus the x coordinates of point P1. So that's it. For example, in this example, it is equal to 2 minus 1, the absolute value of that, plus the absolute value of 2 minus 2, plus the absolute value of 0 minus 3, which you can see it is equal to 4. But now let's talk about the Euclidean distance. And the Euclidean distance is very similar to L2 norm. You can see that it is the square root of the summation of the absolute value of delta xi to the power of 2. For example, in this example, it is equal to the square root of the absolute value of 2 minus 1 to the power of 2 plus 2 minus 2 to the power of 2 plus 0 minus 3 to the power of 2, which if you calculate all this stuff, you can see that it is approximately equal to 3.162. And also we can generalize this type of distances, and we can define something called Minkowski distance, which, for example, it is equal to the summation of the absolute value of delta xi to the power of p and the whole term to the power of 1 divided by p. So this is called the Minkowski distance, or sometimes called the norm p distance. That's it. And for example, in this example, if you want to calculate the Minkowski distance when p is equal to 3, for this example, it is equal to the absolute value of 2 minus 1 to the power of 3 plus the absolute value of 2 minus 2 to the power of 3 plus the absolute value of 0 minus 3 to the power of 3, and the whole term to the power of 1 divided by 3, which if you calculate all this stuff, it is approximately equal to this one. So now let's talk about how to calculate these distances. So this is point 1, so I simply type np.array, and the coordinates of point 1 is 1, 2, and 3, and let's copy this. And the coordinates of point 2 is 2, 2, and 0. That's it. And if I want to calculate the Manhattan distance, I should simply type P2 minus P1, and I should pass order equal to 1. So if I run the code, you can see that here is the Manhattan distance of these 2 points. And if I want to calculate the Euclidean distance, I should pass 2. And if I run the code, you can see here is the result. And if I want to calculate the Minkowski distance, when p is equal to 3, I should pass order equals to 3. And if I run the code, you can see here is the output. So now let's talk about the Frobenius norm and how to calculate that in Python programming language using the NumPy package. So take this example. As you can see, here is a matrix which is called X, and we want to calculate the Frobenius norm. In order to calculate the Frobenius norm, here is the formula, and it is the square root of the summation of each element in the matrix to the power of 2. For example, in this example, it is equal to the square root of 1 to the power of 2 plus 2 to the power of 2 plus 3 to the power of 2 plus 4 to the power of 2 all the way up to plus 9 to the power of 2, which if you calculate all this stuff, it is approximately equal to 16.88. So now let's calculate this in Python. As you can see, we have imported NumPy as NP, and also here we have defined our matrix. This is the first row, the second row, the third row. So we want to calculate the Frobenius norm for this matrix. In order to do so, I simply type np.linear algebra, and remember that NumPy has different sections for different stuff, and one of those sections is the linear algebra section, which is used for dealing with linear algebra stuff. And I want to use the norm function, and I want to calculate the norm of x, and the order which I want to pass is FRO, I mean Frobenius norm. That's it. And I want to store the results in a variable, let's say called results. And if I print the results variable, and if I run the code, you can see here is the result, which is the Frobenius norm of matrix X. And also remember that if you don't pass anything for the ORD argument, the default argument for ORD for the matrix is Frobenius norm. So once again, if I run the code, you can see we get the same output because the default argument for calculating the norm of a matrix is the Frobenius norm. Now let's talk about how to generate random matrix of integers in NumPy. For example, suppose that I want to generate a 3x3 matrix like this, which all of its elements are random numbers between, let's say, 1 to 6, for example. In order to do so, I simply type np, which is the alias name for the NumPy package. Then I want to use the random module, the random section of this NumPy package. So I want to use the random module of the NumPy package. And then it has different functions. And one of those functions is the randint function, which generates random integer numbers. So I want to generate random integer numbers between 1 to 6. So the lower bound is 1 and the upper bound should be 6. But remember, you should write 7, not 6. Why? Because this value is exclusive, not inclusive. Then you should pass another argument called size. And for example, here you want a 3x3 matrix. So you should pass size equals to 3x3. And for example, you store all the results in a variable, let's say called x. And if you print the x variable, and if you run the code, you can see here is the result. And remember, whenever you run the code again, you will get different results. It is possible to get different results. So as you can see, it is going to change every time I run the code. Now suppose that I want to generate 3 random integer numbers between 1 to 6, not necessarily a matrix of random integer numbers. In order to do so, suppose that I want to generate 3 random numbers, so I should pass size equals to 3. It means generate 3 random numbers between 1 to 6. And also, you can write it this way as well. So you can write it this way as well. So if I run a code, you can see here is the result. Now let's talk about how to generate a random number between 0 and 1 in Python NumPy. In order to do so, that's very simple. We can simply type np.random. It means from the NumPy package, from the random section of this NumPy package, I want to use a function which is called random, which is used for generating random number between 0 and 1. And I can pass an argument called size. For example, suppose that I want to generate a 3x3 matrix, which all of the elements are random number between 0 and 1. So I should pass size equals to 3x3, and then I store the results in a variable, let's say called x. And if I print the x variable, you can see here we have a 3x3 matrix, which all of the elements are random number between 0 and 1. And if I run the code again, you can see whenever I run the code again, it is possible to get different results because it is totally random. Now let's talk about how to generate a random array of floats between a range of numbers. For example, suppose that I want to generate a 3x3 matrix, which all of the elements are random float numbers between 2 and 5, for example. In order to do so, I simply type np.random, and I simply use the uniform function, and I should pass 2 and 5, which is the lower bound and the upper bound, and I should pass another argument, which is the size of our matrix, of our array. So for example, suppose that I want a 3x3 matrix. After that, I store the results in a variable, let's say called x, and if I print the x variable, and if I run a code, you can see here is the result. But now you may ask, how can I generate random array of floats between a range of number with limited decimal digits? For example, 2 decimal places in Python NumPy. In order to do so, first let's cut this, and I simply type np.round because I want to round all this stuff to 2 decimal places. And the stuff that we want to round is the thing that I have cut. So this is our matrix, and we are going to round that matrix up to 2 decimal places. That's it. And now I'm storing that in a variable called x, and I'm printing the x variable. So if I run a code, you can see now we have generated random array of floats between a range of numbers, let's say 2 and 5, with limited decimal digits. And now let's suppose that I want to generate random numbers from normal distribution in Python using the NumPy package. Suppose that I want to generate random numbers from a normal distribution with mean equals to 1000 and a standard deviation equals to 5. That's very simple. In order to do that, we simply type np.random. It means from the NumPy package, I want to use the random section of that NumPy package, and from that section it has different functions, and one of those functions is the normal function. So first of all, I should pass the location, which means the mean of our normal distribution. So the location is our mean, so I should pass 1000. And the scale parameter, which is the standard deviation of the normal distribution, is 5 in this example. And also, for example, suppose that I want to generate a 3 by 3 matrix from normal distribution. I want to generate a 3 by 3 matrix which all of the elements are random numbers from normal distribution. So I should pass size equals to 3 by 3. And then I store the result in a variable, let's say called x. And now if I print the x variable and if I run the code, you can see here we have a 3 by 3 matrix which all of the elements are from normal distribution. So if I run the code again, because it's totally random, it is possible to get different results. Now let's talk about the shuffle function. And what do I mean by shuffle? As you know, the meaning of shuffle is rearranging in random order. Reordering in random order. So suppose that I have an array which is called x and it contains a couple of numbers 1 all the way up to 5, and I want to shuffle, rearrange in random order this array. In order to do so, I simply type np.random. It means from the NumPy package, from the random section of that NumPy package, I want to shuffle, use the shuffle function in order to shuffle x. And after that, I should print the x variable. So if I run the code, you can see now we have shuffled our array. So because it's totally random, if I run the code again and again, it is possible to get different results. And we should remember a very important note, and that note is the shuffle function does all the stuff, does rearranging in random order, quote unquote, in place. So when I say it does all the stuff in place, it means this shuffle function doesn't return anything. And because it doesn't return anything, if you store the results of this line in a variable, let's say called y, and if you print y, you will get none. So you can see if I run a code, I get none. Why? Because the shuffle does all the stuff, quote unquote, in place, and it doesn't return anything. But now let's talk about the permutation function in NumPy Python. The permutation function is very similar to the shuffle function, but as you know, the shuffle do all the stuff in place, but the permutation is not going to do all the stuff in place. It is going to return something. So if I want to use the permutation function, so I want to permute this array which is called x, and remember that this function does not all the stuff in place. It is going to return something, and I want to store the output of this function in a variable, let's say called y. And now if I print the y variable and if I run the code, you can see here is the result, and because it's random, if I run the code again and again, it is possible to get different results in every one. And also there is another interesting thing about the permutation function which I want to talk about, and that thing is if you pass a number, for example let's say 4, then the permutation function is going to permute the range of 4. So let's run the code, and after that I'm going to explain the output. So you can see here's the output, and if I run the code again and again, it is possible to get different results. As you can see, it is going to permute the range of 4. So when I pass a number to the permutation function, it is equivalent to passing range of that number. It is equivalent, for example, in this case, in this example, it is equivalent to passing range of 4. And as you know, range of 4 is 0, 1, 2, and 3. So when you pass 4, it is going to shuffle these numbers, 0, 1, 2, 3, which you can see here. So passing a number to permutation function is equivalent to passing range of that number to permutation function. That's it. So now let's talk about the NumPy choice function. So as you can see, I have defined a variable called x, which is an array of a couple of numbers, 1, 2, 3, 4, 5. And let's suppose that I want to choose one number randomly from this x variable. In order to do so, that's very simple. I simply type np.random. It means from the NumPy package. I want to use the random section of that NumPy package, and then I'm going to use the choice function because you want to choose something from x. So first of all, we should pass our array which you want to choose something from. So I want to pass x because I want to choose something from our x variable. Then we should pass the size. It means how many values do you want to choose from x. So for now, suppose that we want to choose one number from x. So that's it. And now if I store the results in a variable, let's say called y, and if I print y, you can see here's the output, which is 4. And if I run the code again and again, it is possible to get different results in every one. Now suppose that you want to choose more than one number from the x variable. In order to do so, you can pass different numbers to the size argument. For example, if you pass 4 and if you run a code, you can see here is the output. But as you can see, it is possible to get repetitions. So you can see we have 2 5s and 2 1s. So maybe you ask, how can I do all this stuff without any repetition? And remember, this is technically called sampling with replacement. And when I say sampling with replacement, means it is possible to get repetitions. But if you don't want to get repetitions, that's very easy. You can pass another argument called replace. So you should pass replace equals to false. It means you don't want to sample with replacement. So if you run the code again, you can see here is the result and you don't see any repetitions. And if you run the code again and again, it is possible to get different results. But remember that you're not going to encounter with any repetitions because replace is equal to false. So now let's talk about the random seed and its concept in the NumPy package, which is a very, very useful topic in random processes. Now let's take this example. Suppose that I want to roll a dice with the Python. So rolling a dice is equivalent to generating random integer numbers between 1 to 6. And suppose that I want to do this stuff in Python and using the NumPy package. In order to do so, that's very simple. I import the NumPy package as np. Then I simply type np.random, and then I want to use a function called randint, which is used for generating random integer numbers. So I want to generate random integer numbers between 1 to 6. So I should pass 1 and 7. And maybe you ask why 7 and not 6? Because this value is exclusive, not inclusive. And then I should simply pass size equals to 3. Because as I have mentioned, suppose that I want to generate 3 random integer numbers between 1 to 6. It is equivalent to rolling a dice for 3 times. And then I store the results, let's say, in a variable, let's say called x. And now if I print the x variable, you can see here is the results. And it is equivalent to rolling a dice and seeing 4 the first time. And the second time you roll a dice, seeing 3. And the third time you roll a dice, for example, you may see 4. That's it. And if I run the code again and again and again, you can see it is possible to get different results. Why? Because it's exactly like rolling a dice, which is totally random, and this process is also random. So whenever you roll a dice, it is possible to get different results. And also, it is possible to get the same results. For example, if you roll a dice and see 6, it is possible to roll a dice and again see 6. And it is possible to roll a dice and again see 6. Of course, the probability of that event is not very high, but it is possible. So this is the reason I use the term possible. So whenever I run the code, it is possible to get different results. Why? Because it's a random process. And now suppose that I'm a teacher of a small class and these are my students, Muhammad, David, Ali, and Alex. And suppose that I want to define a homework for these guys and they're going to do their homework. And for doing their homework, they need 3 random numbers between 1 to 6. And this is not an imaginary example, this is a real example. Because as you know, there are some subjects like, for example, bank queue simulation, which, for example, in this subject, students want to simulate the bank queue. And in order to do their homework, they need, for example, 3 initial random numbers from the normal distribution or whatever distribution it is. So generally, in order to do their homework, they need to start with, for example, let's say 3 initial random numbers. And suppose that I, as a teacher, ask the students to, for example, generate 3 random numbers and do their homework based on these 3 numbers. So as you can see, for example, Muhammad goes and runs this code, and if he runs the code, for example, he gets 625. And David runs the code again, he will get, for example, something like 515. And for example, Ali runs the code again, and he will get 325. And Alex, for example, would get something like this. So as you can see, every student is going to get different results, is going to get different random numbers. And for me as a teacher, it's very difficult to check their homework because every one of them is using different initial values for doing their homeworks. And also there is another problem. For example, suppose that David runs the code and gets random numbers like this, 2, 3, 1. And even if David himself runs the code again, he will get different results. So it is not consistent, it is not repeatable. So even David himself cannot repeat his process. And in order to handle this problem, we want to use something called random seed. And please remember that explaining the meaning of random seed takes time. So if you don't understand the meaning of random seed at first, don't worry about it. You are going to understand that completely by the end of the video. So I can ask the class, I can ask the students to use random seed equals to, for example, let's say 42 or whatever number I want. But for example, let's say 42. So in order to do so, they can simply type np.random.seed, and for example they should pass a number, and for example suppose that I have told the class to pass 42. So if every of them pass 42 to this random seed, and if they run the code, they will get something like this. And if they run the code again and again and again, and if they run the code thousands of times, infinite number of times, they are going to get the same results. And now it is reproducible. So the general idea of using random seed is to make all this stuff reproducible, make something repeatable. So you can see that now every one of the students in this class can reproduce this result of generating random numbers, and all of them are going to get 4, 5, 3. So not only they are going to generate random numbers, but they are going to generate consistent random numbers, reproducible random numbers. So as long as anyone passes 42 to numpy.random.seed, they are going to get the same results. But for example, if anyone passes another number to numpy.randomSeed, for example, suppose that someone passes 0 to numpy.randomSeed, and if he runs the code, he will get something like this. So based on the value you pass to numpy.randomSeed, you are going to get different results. But as long as you pass the same number to numpy.random.seed, everyone in the class will get the same results. In order to better understand the concept of random seeds, suppose this process of generating random numbers, which is a random process, consider this random process as an algorithm, which if you pass an initial value to this algorithm, you will get the output. So for example, if you pass to this algorithm, if you pass a value, an initial value, for example, equals to 0, then you are going to get the corresponding output. And as long as you pass 0 to this algorithm, you are going to get the same output. But if you change the input, for example, if you change the input from 0 to 42, you are going to get different outputs. So as long as you pass the same input to this random process, to this algorithm, you are going to get the same output. For example, in this example that we have talked, if you pass random seed equals to 0, then you are going to get 5, 6, 1 for generating 3 random numbers. And if you pass random seed equals to 42, you are going to get 4, 5, 3. But remember, as long as you pass 42, you are going to get 4, 5, 3 every time you run the code. But if you change the value, the input value, the initial value, the random seed, then you are going to get different results. But as long as you input the algorithm, the same value, you are going to get the same results. Now I really suggest you to watch this video which is on the screen now.